Well, so this is the recurring theme of today's talk. It will keep on appearing. And so mapping spaces appear across mathematics everywhere. And we will consider some specific examples today. And so what we will do with those examples is that they will typically be some algebraic object defined over the integers. Like think of some polynomial over integers cutting some space out, and what one can do is one can reduce modulo p to q there, reduce modulo q to get like x over fq, and one can ask the number of points here, but one can also take the complex points by extending the scalars and consider this. Well, usually it won't be a complex manifold necessarily, but it's some complex algebraic variety, let's say, and ask about the topology, particularly what is cohomology or homology is. And thanks to this, we'll treat it as a black box, away conjectures, which hasn't been conjectures for a while now. But thanks to that, we can switch back and forth between this guy and, well, this guy. What we'll also try to do, sort of, is to see whether we can, when we try to talk of topology of this complex variety, whether we can do the homology operations for the variety over any algebraically closed fields in equal footing. So, so if you don't know what the algebraic homology is, that's perfectly fine. Take your favorite algebraic variety, think of it over complex numbers, think of the singular homology. Right, so these two guys versus this guy. But we'll play this whole game with mapping spaces instead of this X. So what sort of mapping spaces do we want to look at? I will start with an old and fundamental example of maps from, so when I say more, it's algebraic morphisms or holomorphic morphisms, take your pick, from P1 to Pn, which are of degree D. So these are given by an n+1 tuple of degree T homogeneous polynomials in two variables having no common zeros. And this no common zeros part is super important because otherwise, if f0 to fn has even one common zero, it will land in like 0, 0, 0, 0, which doesn't belong to Pn. So before we see what we want with this space, I want to give an idea about what it looks like. So you have this guy is, so all these polynomials, each is determined by d+1 coefficients. So if there was no condition on the zeros, like having common zeros or not, this would be contained in this big projective space of dimension, what? This, where like the complement is precisely locus of these tuples such that they do have a common zero, have at least one common zero. Right? So this is a Zariski open-dense subset of this projective space as a complement of a complex codimension 1 subvariety, closed subvariety in this projective space. So that's a pretty big space, all things considered. And what Graham-Siegel did in '79 is that he proved this space is actually homotopy equivalent to, so here we're considering algebraic or holomorphic maps, right? So if you forget about them and just take continuous maps from P1 to Pn, then they're homotopy equivalent up to a certain degree. And that sort of started many investigations into mapping spaces to try to see whether there is whether this guy P1 to something, let's say Y, is homotopy equivalent, weak homotopy equivalent to like continuous maps. Let me write map. So this is the two sphere. What Siegel actually did, there's tiny condition I need to put in. So you see that like not just take this space, but take the based maps. So suppose you pick a point on P1, let's say infinity, and you saw like infinity goes to some fixed point in Y. So in the case of Y equals Pn, the projective space, let me write star for based stuff. Based maps. Now the question then becomes, how far can one push this? On a different direction, one can also ask, okay.
Siegel computed both sides independently and showed they're the same. Is that how you do this?
No, Siegel took the forgetful map, forgetting the algebraic structure.
Yes.
And showed that that's a weak homotopy equivalence up to a certain degree.
But by kind of independently computing the topology of both sides and showing that they match under this map. I think what I'm asking is,
he didn't compute the independent homology, if that's what you're asking.
He didn't compute that?
He didn't compute the independent homology on both sides of that's.
Okay, I'll ask my question later.
Okay. So if one wants to now forget the complex numbers and wants to do some homology or cohomology computation or any algebraic closed field, and like maybe expect that they are the same, well, one can't exactly talk about this sort of setup anymore, like just take continuous maps. And furthermore, being able to answer things for like FQ bar would be interesting, because one would be able to answer things of arithmetic nature, like how many smooth degree-free rational curves are there in the projective plane over F5. So the projective plane over F5, one can count the number of degree-free curves, all right? That's some polynomial in like 2 to the 2. I shouldn't try to compute this, but its dimension is easily computable. But the restriction that it has to be smooth and rational makes it tricky. And thanks to the Weil conjectures, if one manages to compute this, one can use what is called a Grothendieck-Lefschetz fixed point formula to get this answer. So how far again can we push these things? One point to be noted is that whatever Siegel did with complex numbers, you can't expect something like that over FQ bar on the nose, but still the homology computations match if one ends up computing both, as it should. So let's generalize things. So instead of B1, instead of the projective line, let's take C to be any genus G curve. Oh, I should say this to keep my slides uncluttered. I have not put, like I didn't put symbols. I didn't define everything over the slides. So if you have questions, please let me know. So C is a geometry curve. Y is just some smooth projective variety, let's say, and consider this the space of degree maps from C to Y. When the genus is, the genus is always going to be bigger than or equal to 0, and Y is in Pn. And unlike in the case before, where Y was, and C was a projected line, where the space was connected, it's no longer, it need not be connected anymore. You could have all sorts of things. So this is a picture for the famous Cayley-Salmon theorem. This is the Klepsch cubic surface, I believe, and there are 27 lines on a smooth cubic surface. So the H0 has rank 27. And so what about other subsets of Pn? And much has been done in that regard. For example, when Y is a low degree hypersurface, there is the amusing paper by Browning and Savin, where they use analytic number theory techniques to have estimates on what this space should be. But this brings us to a general conjecture that's attributed to Cohen, Jones, and Siegel, that for any Y, which is a Fano variety, if you don't know what a Fano variety is, think of like a, I'm not sure whether I should say this, but a close approximation of the projective space. So it's anti-canonical bundle example, but leaving canonical bundles aside, it should have like, it should admit maps from P1 at least. And on the same note, whether we can say what more generally the analytic homology is for maps, for algebraic maps from a genus G curve to Y. Okay, so this brings us to another related conjecture, the geometric Manin's conjecture. I'll just state the version that's going to be useful for us. So FQT, so this is a global function field, points in Y of height h has to do with the FQ points of this mapping space. And what geometric Manin estimates is that says it's supposed to be Q to the dimension of this. It's supposed to be dominated by Q to the dimension of this mapping space. So this is sort of I believe in a symptotic result when Q grows bigger. Like you want to say that when Q grows bigger, the Q to the dimension is what matters. Okay, so now I will go into an example and see what results we get. So before that, any questions or comments, suggestions?
This is a statement or conjecture or?
Geometric Manin's conjecture, or at least the version that I'm using is this, yes.
So usually that requires a variety be
Fano, yes.
Fano or something.
Yes, yes. So yeah, I should have, to keep the slides uncluttered, I left many adjectives. So henceforth, just think of phi as a Fano. Phi should be a Fano variety. If you don't know what a Fano variety is, think I'll give some examples. Say, one thing that looks at projective spaces, weighted projective spaces, toric varieties, Riemannians. So, I believe. Right. Henceforth. Anything else? Okay. So the example I want to talk about now is that let M11 be the moduli space of genus 1 Riemann surfaces with a marked point. So that's a picture, or at least I tried. And C11, that fancy C11 is supposed to denote the total space, and what that is not what I wanted. Okay, so what this is the elliptic. This is the genus 1 Riemann surface with like one loop squished, which is standing at the point at infinity. And what happens is, so the moduli space of genus 1 Riemann surfaces with a marked point can be thought of as C via, for example, the J invariant, and its compactification has this nodal curve at infinity. So M11 bar is sort of like CP1, and I say sort of because in reality it's actually a weighted projective stack P46. If you don't know what that is, think of CP1, that's fine. And now a map from a genus tree curve C to M11 bar will determine a stable elliptic fibration on this genus tree curve, right? So be it C equals P1 or be it C for some higher genus tree, you can ask how many, or whether you have estimates on the number of stable elliptic fibrations over a particular finite field. And that shouldn't be a blank slide. Okay, yeah. So in the case, I have just stated the case of C equals P1 because for general C, the answer is long and takes 2 many slides. The elliptic cohomology, and just replace M11 bar by CP1 if you want, QL by the rational numbers, takes singular if that helps, and this is like QT modulo T squared. And this is the cohomology degree and the weight given here. The takeaway for this sort of results is that, like, no matter what D is, this is the cohomology that you get. And one might think why I have used this exterior power notation. There is a small reason behind it. It's that, so instead of M11 bar, you can, like, whatever the actual theorem is, one can consider like any weighted projective stack, and instead of P1 or instead of a genus tree Riemann surface, one can take actually higher dimensional projective spaces as well and get some sort of, not exactly full cohomology result, but some low degree or stable cohomology. And in turn, one gets point count estimates. And in the special case, it becomes Q to the 10D minus Q to the 10D minus 1. So Q to the dimension of the space terminates. And this verifies the geometric mapping for not just M11 bar, but any weighted projective space fully, following the same method or the same strategy of proof. Any questions so far?
So 10D is the dimension.
Yes, 10T plus 1 is the dimension.
And do you happen to know what the discriminant of the corresponding elliptic curve is?
I mean, degree. So degree maps from P1 to M11 bar would translate to like the height being 12T.
12D. Q is 12D. Okay,
Yes.
good. Yeah.
Okay. So one thing to observe is that whatever this result is, it absorbs Siegel's result, but it doesn't go via the world of continuous maps, sort of can't. Okay, so I want to sort of generalize the weighted projective stack strategy to complete simplicial toric varieties. So now we are talking about So complete simplicial toric varieties are final. And so the goal would be to ideally have at least a homological stability result. So low degree cohomology compared to the dimension for the space of morphisms from a genus G Riemann surface C to this P sigma. So what is sigma? Sigma is the rational polyhedral fan. N denotes the number of rays of it. T and epsilon1 and epsilon up to epsilon t, these are invariants of sigma. So what I haven't written here is T has to do with the number of primitive collections of P sigma, and epsilon, these epsilons are the size of each primitive collection. If you don't know what that is, just think of it as some combinatorial invariant of some toric variety. And now the degree is not just determined by a single integer, it's a degree vector. It's d1 to dn, actually the same n as the number of rays. And the theorem is that the cohomology, and again, I'm stating it only for P1 and not for a general curve because that wouldn't fit in one slide. So the theorem is that this is a full cohomology ring where d1 to dn, I wrote the n right. Yeah, so d1 to dn are actually the generators of cohomology of P sigma itself. And modulo a certain ideal I and these other generators Zj. So the ideal I is generated, so that it can be completely described by generators and relations. I mean, it is described by generators and relations, and which are like entirely in terms of T and epsilon i's and the D's. And yes, one does know at the same time what the weight, what the Hodge type, stuff like this are. And in turn, this makes it easy for point count purposes. And
So can you say what the D's are again? Are they explicit?
these are the generators of P sigma. So the cohomology of P sigma is given by its each ray has a divisor corresponding to it. So
Right.
these are the generators of that cohomology. Actually, the structure of this I, which I haven't written down because again, too big, but the structure of I is very close to like the ideal you go modular by for the cohomology of P sigma. And also, it's super important that we take complete simplicial toric variety. Like dropping these adjectives would make this theorem not hold for sure. Among other things, when you drop these two adjectives, the cohomology of a toric variety is no longer just a combinatorial invariant. So here is some point count results, or rather coming up, which is entirely determined by some nice combinatorics. And when P1 is replaced by a higher genus curve, you still have Q to the required dimension dominating, and the rest of the unstable part of the cohomology can be estimated to not ever overpower Q to the n. Okay, any questions so far?
Sorry, on the previous slide, yeah, can you say explicitly what so the DIs are
the DIs are the generators of the cohomology of P sigma.
so I can think of them as divisors.
Yes.
P sigma.
That is
But
it.
how do they? Can you explicitly?
ZJ?
No. Could you say how they get? Is it possible to easily say how they give classes in H2 of this mapping space? Do they correspond to divisors on the mapping space?
They do correspond to divisors of mapping space. I was going to say this is not the best answer, but I was going to say, like when this is just a projective space, one has, I mean, yeah, mean, the answer would be to, I mean, if I try to answer this, I would get into the computation, which is probably not the right movement. But I can explain this later. Anything else? Okay. Right. So just a remark that I made earlier, that similar results hold for P1 replaced by C, some hierarchicus curve. And this verifies the geometric Manin for complete simplicial toric varieties over global function fields, which are function fields of Riemann surfaces. So now the question is, what are the technical difficulties to compute something like this, especially given the strategy that Siegel set up back in '79? So one thing that the key ingredient behind Siegel's proof, which was used by people afterwards as well, like people, so Guest used Siegel's technique for computing more the cohomology, for computing this cohomology, not the whole of it, but like up to a certain degree, using Siegel's technique. But the catch is that what Siegel uses is something called a scanning map, and that is a very that's a technique that holds only when you're over complex numbers, and you can take like tiny balls, tiny neighborhoods, and it's a very analytic topology technique, which is beautiful but has its limitations, because in our case, the target is either not even a variety, or it can be singular, because complete simplicial toric varieties can be singular. And so not only Siegel's techniques do not work for these cases, they also don't, they are not applicable for positive characteristic situations. I recently found out, though, after I made up the slide, is that a person, Geoffrey Horrell, has like a motivic analog of scanning maps, which might help in like translating the scanning map business to positive characteristics, but I'm not defining scanning map in this talk at all. And we don't know yet whether it works, but it's an interesting question for sure. Okay, so what goes behind proving something like, what goes behind constructing a general strategy to prove either of these theorems? So before I get into the proving question or comments, okay, so some morphisms from C to Y, where again, remember that Y is a weighted projective stack or a complete simplicial toric variety. But even in general, if I can write this morphism space as like X minus Z, where at least X is something good in the sense that something whose cohomology is tractable, and Z is, well, if not good, then maybe it can be replaced by something good. So just a quick example, in the baby case, when if one takes just maps from P1 to P1, as I explained here, the resultant locus is precise. The resultant zero, the resultant non-zero locus, the resultant of two polynomials being non-zero, is precisely the case where you get a morphism from P1 to P1. So its complement is the resultant zero locus, which is nasty, really, because it's a determinant of this really big matrix, and so its zero locus is given by it's some incredibly, like, it has a lot of singularities and a complicated subspace of the projective space. So what the idea is that we do use cohomological descent, but like a modification of it. I will briefly gloss over what the modification is, but not too much. Okay. So I want to give for those who haven't seen cohomological descent before, I want to give a quick overview of like why it helps, or why it's something that can be considered when you have really nasty spaces. Okay, so recall Nernst theorem, which so M is supposed to be a nice topological space, and you have an open cover. Each UN is contractible when the check nerve given by these vertices and syntheses. This is a combinatorial object, and this the posit topology of that is homotopy equivalent to that of the space M. This should not be S, this should be M. I have misused S a few times in this slide probably. So that's Nernst theorem for us. But now what we want to do is, or sorry, what rather Grothendieck did was, well, let's ignore being nice or not, but like we don't require UN to be contractible anymore, so that's gone. We keep removing conditions, UN is not even open anymore. And now you're like, okay, can UN at least be subsets of the base space? But you don't need that either. Okay, so we somehow want to have something like a Nernst theorem, but far less restrictive. And this gives us a definition of a cover of M where, yeah, I should pull up the whole cartoon because it's easier to see there. So you take like, so cover is just like maps from spaces to the base space. And intersection of these is given by fiber products, which if you think about these spaces, when they are subsets of the base space, S is M. So fiber products give you precisely intersections of these open sets and internally nerve. So of course, this begs the question about like how to define homotopy equivalence and such. I won't get into that, but the point of this cartoon is to show that Nernst theorem, something as basic as Nernst theorem, can be beautifully generalized. So in our cases, so this, I'm going to say some more words about the proofs, is so typically we have bad Z. Remember that the Z was the resultant zero locus in the case of maps from P1 to P1. And the good T is suppose one can think of resolution of singularities. And if you take U0 to be T, I define the successive UN to be just taking the check cover. And it looks like taking fiber products like these should complicate the cohomology, but this modified cohomological descent, what it does is it gives this quasi-isomorphism where F is suppose a sheaf on Z, and this symbol means that you take the sign action of the symmetric group on this guy. So traditional cohomological descent would have just this part, but this modified version incorporates this guy.
I'm getting confused as to what's completely general for an arbitrary Y in this kind of descent, and where you're going to use very much group theory, like projective space toric variety, or I don't know what your other examples are.
Right, so the thing is the apparatus to cook up a spectral sequence holds for like whatever C, whatever Y, doesn't matter. But then the question is how computable it is.
It's only when you come to compute.
Right, and I am only going to sort of point towards a spectral sequence and not to any computation after that.
And you will clarify what your Y's are. Or they're just these examples.
They are these examples for mapping spaces, but these also hold, this apparatus also holds for like more like things which are not mapping spaces, but they have this common thread of being configuration-like in a sense, which is in the beginning sort of what made Siegel scanning techniques possible. But I'm not going to talk about the general examples, if that's what your question is.
So does do you get a statement also, let's say with Z mod P coefficients, or does this
No, it's
modify?
rational coefficients. The statement is with rational coefficients, like Q or QL.
And is that because this modified descent
Yes.
doesn't work well with Z mod? Okay.
Yes. I mean, there will be Tor groups with symmetric groups and all that.
Okay.
So, to remove that. Right, so going back to the toy case of maps from P1 to P1, I want to sort of, whatever I wrote here looks like a bunch of symbols without really applying anything. So I want to at least show that these spaces are not as nasty as it might seem at first glance, and like show them through the toy case of maps from P1 to P1. So Z was this, the resultant zero locus, and I want to define T, the normalization of Z. So it's recording one common zero at least. Ft equals Gt equals 0 should be there. Sorry. And Un, so U0 is this T, and Un, which is essentially extracting n plus 1 common zeros, is giving us so the upshot is that the modified descent over the space UN, where UN, I mean, so Z was bad, but when Z is replaced by UNs, you can still sort of do a version of a nerve theorem with very nice spaces. These UNs are nice in the case of maps from P1 to P1, because these T's are all like points in P1, and this FG, these are like lower degree polynomials. So essentially, UN is like product of a bunch of projective spaces, which is super computable.
Sorry, can you just
So you're working with the fixed degrees of f and g?
I am working with a fixed degree of f and g.
So in P, is f of p equals g of p equals 0?
0, yes, I missed that. I'm sorry.
Ah, okay. Good.
Yes. So U0 is ft0, gt0 being 0, and just a t0 is t. Yeah. So, in fact, in the case of the maps from P1 to P1, if we go back to this isomorphism here, it's actually like honest to God isomorphism of like, so these are like the maps are finite, these are honest to God sheaves. One doesn't even necessarily need the language of cohomological descent. Just in the language of sheaves, one can check out the level of stars and get by. But suppose if you're interested in things like your domain being higher dimensional projective spaces, then you specifically need this modified cohomological descent machinery. Okay, any questions so far? Right. This is supposed to be my last slide because I did not expect to go through all this so fast. So I will take a while to come to my last slide and talk about the other examples where the same technique works and why. Okay. So So the maps from P1 to P1 shows that some sort of extraction of common zeros gives you a nice tractable hypercover, or a nice tractable like fiber products. It's a nice space, and one can try to fit this in situations like, say, so suppose you have X is a smooth predictive variety. And suppose you have L to be what is called an M very ample line bundle. Now you can ask about the topology of the smooth locus, like the locus of smooth sections. Or more generally, you can sort of impose a Taylor condition on those sections and ask about the locus and try to understand, among other things, the stable cohomology of it. And a priori, this doesn't have the extraction of zeros structure, but if you consider so inside this you have the space of smooth sections, let's say. And one can still write something like, so T would be, by this strategy, so take one element from your variety X and a section S, a global section, such that the multiplicity sort of vanishing is of order at least 2. And if you define UN to be the standard check cover, but instead of that, instead of considering the standard cohomological descent, if you take the modified cohomological descent by incorporating the action of the symmetric groups, then there are 2 side effects of that. A, your resulting spectral sequence gets chopped off, and the computation, like an order n computation, reduces to something like order 1. And B, and B, these entities like R, pi lower star, pi upper star, with like twisted by sign, is these have this is the associated gradient of I started off in a really bad place. Okay. Of something called the derived indecomposables. In the sense of, so I won't define this because that will take me too long, but in the sense of Galicius, Coopers, and Razzle-Davies. So the upshot is the option of considering, so the point I'm trying to make is that the option of considering this modified cohomological descent is twofold. One is having an easier spectral sequence to deal with, and two is being able to relate to the language of derived indecomposables, and without defining what it is, I will say why that might be something useful to consider in the next page. So hold that thought. Right. So for higher order homological stability, homological stability is about understanding low degree cohomologies compared to when the space grows bigger. Now there is the unstable part where we don't typically have a whole lot of control about, but to study the patterns in that unstable part, what Galatius, Coopers, and Randolph Williams developed was this language of derived indecomposables to understand them. And being able to use the modified cohomological descent, one expects to have an understanding potentially of the higher order homological stability in the sense that patterns in the unstable cohomology. So, which finally leads me to the last slide, which is a list of like questions that are potentially vague and definitely open. The first one is well known, and I believe the third one is something that I have talked about earlier, and just to recall what it is, it's about comparing the space of algebraic maps with the space of continuous maps, and asking whether there is at least a weak homotopy equivalence, maybe stably. And lastly, the question of patterns in the unstable homology of these spaces. So to wrap it up, one can always take modified cohomological descent for like whatever function space, like whatever situations where you want to know the cohomology of the open part, but the closed part is bad. But the question is whether that spectral sequence will be any useful. Whether they will be useful or not depends a lot on the geometry of the spaces. In our cases, they were complete simple toric varieties and etc. But like if you have, specifically, I want to highlight this fact that if you have Y to be like a low degree hypersurface, you do not get something like what Brownian-Salin has, because the spectral sequence doesn't give you anything computable. So I should stop here. Thank you.
Any questions for the speaker?
I have two. One is basically Akshay's original question. It seems that in a topological world, not the descent and Grothendieck world. Yeah.
Sorry?
In the topological world where Siegel's theorem, that's a homotopy equivalence.
That's a stable homotopy.
Stable. You in this Grothendieck setting where you're doing this descent and these nerve constructions, the comparison is only cohomology.
The comparison is only homology.
Okay, that was, I guess, was his first question. I'll clarify that. Then the last question, the last statement, if you're a hypersurface, and you're looking at morphisms into a hypersurface, so you can be able to complex numbers. You said something about a low degree. You can, and then you said you can't or can complex.
You cannot. I mean, in the sense that you can cook up a spectral sequence, but it'll be.
But they are known,
useless.
but I guess one can still count. I mean, there are many cases where you can do that still if you're low degree. You can even use the circle method as Browning and Savin.
Yeah, what I'm saying is that if you use that modified cohomological descent,
Yeah.
this particular quasi-isomorphism will hook up the resulting, like this particular hypercover, particular quasi-isomorphism and the resulting spectral sequence, you will get terms like lower degree maps from P1 to the same hypersurface, which is like what Browning and Savin do with the circle method is entirely bypassing the situation, right?
I just was perplexed by them using the circle method quite cunningly. So I'm just asking you. Yeah, they're using a method to find sections, yeah, which is harmonic analysis method.
Yes, so their estimate, so more specifically, their estimate like maps from like A1 to like an affine hypersurface.
This is what they do.
Yes, and so that, like, they have a spectral sequence that converges using the circle method. They have a spectral sequence that converges to this, the cohomology group of this, like maps from the affine line to, and that in turn will fit into this spectral sequence to give some complicated. Is that a thing? Three-dimensional spectral sequence or something? I don't know. But yeah, but like each term of the spectral sequence you get from. What is it? So each term you get from each term of the spectral sequence you get from this is the target of another spectral sequence that they have, is what I'm trying to say.
I just have a small comment. I think your toy case, it should your second last slide. What you should call that, it's a categorification of the sieve. It's very parallel to the way the sieve works, the analytic number theory.
Okay. Okay. I'll make a note of that. Thanks. Okay.
Any other questions? Let's thank you again.